Hey, Katie.
Hi, Ben.
Hi, guys.
Whoa, who's that? You are listening to Linear Digressions. Okay, so it's been a while since we had someone on the episode, so I wasn't actually surprised to hear Tim's name. But
We're talking with Tim today. Hi, Tim.
Hi, Katie. Hi, Ben.
and this is Tim, head of fairly well known for Scikit-Optimize, which is an open source project up on GitHub that a lot of people have found quite useful.
So the connection here is that Tim and I actually go back a long ways, years. We knew each other at CERN, and now Tim is off doing much more useful things than trying to find particles. That's an unfair thing to say. Tim, why don't you give yourself a quick introduction and let everybody know sort of like where you came from and where you're going.
Like you said, I used to be a particle physicist and worked at CERN. And recently I decided to leave and stop being an academic. And now I work as a freelancer, help people who have data and want to do science with it. So I do, lots of programming, lots of machine learning, this kind of stuff. And I work, like you said, on a project called Scikit-Optimize, which we started with some friends from CERN and some people I met from a different open source project.
And I think this is really cool. So a lot of people are probably familiar with Scikit-Learn.
And if you haven't heard of Scikit-Learn, it is a set of tools that you can use for machine learning in Python that a number of people have found very useful.
Yeah. So, Tim, I was wondering if you could say a few words about why you and the people that you're working on Scikit-Optimize with, why you guys decided to go out and do this package. And maybe a related question is, what are the problems that you're trying to solve that aren't already addressed in Scikit-Learn for the people who are familiar with that package?
So Scikit-Optimize is really an attempt to build or implement a set of algorithms which you can use to optimize functions which are very, very expensive to evaluate. So you talked about doing hill climbing and so on. And now imagine that the function you're trying to optimize or find the maximum of requires you to go away and do an experiment in a lab, and then a few weeks later you come back with the answer for that one point. And now the algorithm says, oh, that's great, please evaluate these other 10 points, and then we will make progress. So Scikit-Optimize is a set of algorithms which try to minimize the number of times you have to evaluate the function if you know nothing at all about the function. So imagine your job is to brew the best cup of coffee in the world, and you have all the equipment, and you don't want to brew thousands of cups of coffee to try and arrive at the best one. You want to make as few of them as possible. So you would use something like Scikit-Optimize, which would suggest after every cup of coffee how to adjust all the settings for the next cup of coffee so you arrive at the best one as quickly as possible.
Besides trying to make the best coffee that you can, what are some of the expensive functions that you were sort of had in mind when you were designing this?
So at CERN, we have very complicated simulation programs that simulate, the Large Hadron Collider and then each of the experiments, and they're incredibly expensive to run, and they have lots and lots of things that need to be adjusted. So that's what we were originally thinking of. How do you make an optimizer that can help you tune your simulation to be as good as possible? The other big use case is people who do machine learning. They need to tune lots and lots of parameters on their machine learning model. And some of these models take days to train, so they also want to have a way of finding the best settings without training too many models.
I did not realize that about that CERN connection, but I'm remembering back to my days in particle physics, and we've talked a little bit about some of the computational tools that they use to do the simulations in physics. But yeah, roughly the idea is you have simulations for the protons actually colliding and then maybe creating some kind of exotic particle, but then usually the exotic particles decay almost instantaneously, and you get things like pions and protons and electrons and stuff that then fly out, and so you have to simulate the process by which those particles are flying around, and then how they interact with the detector, which, as it turns out, as I recall, was actually the most expensive part of it, was simulating the interactions of these decay particles with the actual material of the detector. And I remember the whole thing, could be really, really expensive because it could take minutes sometimes to do each event, and then you have to do tens of thousands, hundreds of thousands, millions of events. I'm curious, are they actually using Scikit-Optimize to speed up that process? Because there seem to be all kinds of inefficiencies in that process, and some of them they were working on making them better with things like FastSim. But yeah, is that the kind of thing that like particle physics is, actively trying to address with stuff like this?
I hope so. Having left, I don't know whether somebody's actively working on it anymore. But this was one of the original motivations for starting Scikit-Optimize back at the beginning of 2016, and then not much happened for a while, and I left particle physics. And
so I think this is really neat. It feels like a very generic thing in a way, because you can use it to describe or to solve problems of particle physics, or you could use it to describe how to brew the best cup of coffee. Basically, any kind of expensive operation that you want to minimize the number of times, like heavily optimized for minimizing the number of times you run it.
So to stick with the example of making the best cup of coffee, how would I do it if I was, put in front of a machine that I don't really know how to operate, and, lots of different ingredients? I would try a few different settings, see what happens, and then I would learn that, grinding the coffee more finely makes it more bitter, and grinding the coffee less finely, more coarsely, makes the taste more mellow. And you start building like a mental model of how changing different buttons affects the taste. And Scikit-Optimize tries to do something very similar. It uses regression algorithms to try and build a model, and uses this then to suggest where you should go next.
So let me ask a related question. So I've played around a little bit with Scikit-Optimize and run some of the examples and things like that. And I know that there are a few different types of algorithms that you have in there. And we don't have to go into the technical details, but just the point is that there's a number of different ways that you might try to explore the space as efficiently as possible. And so walk me through what you, as someone who's building this library, like what are the metrics that you encourage people to use for figuring out which of those algorithms might be the best?
So one neat thing is that we try and implement several different optimization algorithms. We try and make benchmarks where you can compare how well each one of them works. And the metric we use is how many iterations does it take an algorithm to arrive at the known optimum of the benchmark problem. Because for all the benchmark problems, we know what the answer is. So we can use it to check how long it takes the different algorithms to arrive there. And then, so different benchmarks test different strengths and different weaknesses. Some have very, very high dimensions in the search spaces. Some of them have really, really complicated shapes. Some have lots and lots of local minima. There's a huge variety, and then you can try the different algorithms on the benchmarks to try and figure out in which cases you want to use option A versus option B. Because for your actual problem, you can't really afford to run 5 different algorithms and see which one converges more quickly. Because if you could do that, then you wouldn't have a very expensive function to evaluate. So the way I think you would pick which algorithm to use is study how it performs on different benchmarks, or read the literature which explains to you which ones are better in which cases, and then try and find the benchmark which is the most similar to the problem that you have, and then go with the winner from that benchmark.
One thing I'm just thinking of right here, an intelligent listener might be listening to this and thinking, is there one best optimization algorithm that maybe we haven't figured out what it is yet, or we haven't even totally devised the algorithm itself, that's always going to be sort of the fastest and the most efficient, which is a totally reasonable and very interesting question to ask. And I was just thinking that, as far as I'm aware, the answer is no, that there's actually sort of a mathematically proven no free lunch theorem in optimizations, which we haven't talked about, but I'm kind of hoping to at some point have a chance to do an episode on it. But basically, there are researchers who looked at this exact problem and mathematically demonstrated that depending on exactly what the problem is, that there's always going to be an optimization problem that does best on it, and that those algorithms are not always going to be the same. Like, you can remember maybe back to people who've taken introductory computer science classes where they're trying to teach you all the different kinds of sorting algorithms, right? And there are many different ways that you can sort a list of integers, let's say. And each one of the algorithms you can think of, there's some input list of integers that's going to make it actually a really inefficient sorting algorithm. So there's no single algorithm that's always going to give you really good performance. It's just there are certain algorithms that usually tend to do better. And so having lots of options on the table, and also a sense of which options are best suited for which kinds of problems, is actually totally the right way to think about it, and not trying to come up with something that's always going to be the best.
Yeah, that's exactly right. So most of these algorithms are invented by somebody, and if you read their papers, very often the conclusion is this is the best, full stop. But in reality, I think it's more like you said, that depending on how exactly your problem is set up, then some algorithms will be better than others, and tomorrow you might have a slightly different problem, and then the conclusion which one is the best one will change.
Tim, what are you most excited about in terms of moving forward with this project, like new things you're building or implementing?
One thing I'm super excited about trying out, because we don't know how well it will work, is to, instead of using one algorithm to solve your problem, can you learn something from the world of decision trees, where it turns out making a committee of several decision trees is actually much more powerful than any single one? Can we make an ensemble of the different algorithms that we have that will be smarter than each one of them separately?
Oh, cool. So it's sort of like ensembling or stacking your optimization algorithms in the same way that you might do with your supervised classification algorithms or whatever.
Exactly, something like this. So I think that would be... we have a GitHub issue for it, and it has a ominous grey label called research.
Is there, as a side question, is like, how easy is it to do transfer learning between these different algorithms? My guess is that they aren't really set up to allow that, but maybe your Gaussian processes start figuring out something interesting. Is there a way to propagate that knowledge, so to speak, over to, let's say, your random forest?
I have no idea.
Okay. Because that would be cool, I'm just saying.
Yeah, it would be very cool, but I have no idea.
Okay.
Awesome. Tim, thanks for joining us. And we're going to have you on the next episode as well to talk more about open source and a bit about what it's like to run an open source project. But for now, if people are interested in Scikit-Optimize, I mean, of course, you can always Google it. That's SCI-kit, not PSY-kit. And are there any other places that people should go looking?
It was great being on the show. And if you are interested in contributing or using Scikit-Optimize, go to scikit-optimize with a z.github.io or type it into Google.
Cool. Well, thank you so much, Tim. Looking forward to chatting a little bit more in episodes to come. But this has been really great to get an idea, not just of how optimization is theoretically used, but to actually see what it looks like on the ground as you're trying to make it useful to people who are trying to solve real problems. Thank you so much for telling us about it.
Thank you.
Linear Digressions is a Creative Commons endeavor, which means you can share or use it any way you like. Just tell them we said hi. To find out more about this or any other episode of Linear Digressions, go to lineardigressions.com. And if you like this podcast, go ahead and leave us a review on iTunes so other people get to listen to this content too. You can always get in touch with either of us. Our emails are ben@lineardigressions.com and katie@lineardigressions.com in case you have comments or suggestions for future shows. You can tweet us at lindigressions. Thank you for joining us, and we'll see you next time.